Well, thanks so much for having me. Like Ariel said, I was originally planning to be in person, but it's the year of 2025 and immigration is just one of those things we think about now. So I'm here on Zoom from Canada, from Montreal. But I'm really, really excited to tell everyone, both in Seattle and online, about Nilearn, or I still call it Nilearn, so I'm just going to call it that. Maybe a tomato thing. But yeah, this is a library that I've been a core developer on since 2019, 2018 or so. So I'm certainly biased, but I think that it's a really powerful library. I think it's a really impactful library for anyone using functional neuroimaging data. And I'm here today to show you a little bit about some of the things you can do with it, both for machine learning with neuroimaging data, which you've heard a lot about machine learning earlier this week from Ariel, among others, and also a little bit of statistical analysis. In particular, I'm going to show you how you can run some general linear models with Nilearn, and then maybe how you can use those general linear models to improve your machine learning. So that's my goal for today. As Ariel said, the original plan wasn't that I was on Zoom, so it's a novel configuration. So if there are any issues, please don't hesitate to either put them in the chat or put them on Slack. And of course, if you have any questions at any point, that's why I'm here. So please don't hesitate to interrupt me. The only thing I'd ask is for the folks in the room. I can hear folks from the crowd, I heard earlier, but it's a little hard to hear like super precise. So maybe either speak loudly or come a little closer to the front. That would be really helpful for me if you have questions, shouting them out at any point. Or feel free to ask them on Slack and I'll just restate them. Awesome. Okay, let's get started. So one thing that I want everyone to check before we get started is I have a series of examples that we're going to walk through. That's really the structure of this tutorial, and they're all loaded in this curriculum folder under DuPre Nilearn. But one thing we noticed recently, is that the Jupyter Hub might not have the absolute latest and greatest version of Nilearn. And I want to show you fun cutting edge things. So I want to make sure we all have the newest version. So the way we can check if you do is, and the way we can get it, is if you just launch a terminal from your launcher, you can type Python. I'm just going to get rid of this so you can see things a little bit easier. Import Nilearn, and then Nilearn.version, double underscores around version, and it'll tell you a value. If your value is 11, or if your value is anything other than 12.0, we're going to need to upgrade Nilearn. So it should all be 11. So what we're going to do is just tell pip install upgrade Nilearn. It'll tell us we've successfully installed Nilearn 12.0, and then we can just repeat, just to be extra sure, the same Nilearn check. Perfect. Okay, so because I went a little fast, for those who didn't see, this is the command to run. Pip install U for upgrade Nilearn. And then things will work. To be safe, I'm actually going to go ahead and put this in the, oh wait, thank you, Noah. I was going to put that in the channel, but Noah beat me to it, so we're perfect. Awesome. Okay, so let's get started. Now that everyone has the latest and greatest, we can show all kinds of fun things. So the other thing I want to point out about the structure of this tutorial is you may notice I have two panes side by side. With the one on the right, this one here is obviously the NeuroHackademy Jupyter Hub, which is beautiful and executable, and it's the one we're actually going to run things in so we can try and experiment with different values. The one on the left is a Jupyter book. This is a website that's built from the notebooks. The reason I want to show this is it just has some really nice rendering that you can see. For example, here you can see that we have a note that isn't quite rendered as nicely in the notebook as it is in the Jupyter book. So I just want to have the two side by side so you can see a little bit of the formatting, so it's a bit easier to read, and then we'll actually execute the things in the Jupyter Hub. You can choose one or the other. They're really the same. It's just the formatting that's different between them, because again, this is a website built from the notebooks. with all of that said, let's get started. All right, so the name, the tomato name, Nilearn. One thing you may notice right away from the name is that it sounds a little bit like scikit-learn, which you may have heard of earlier in the week for doing machine learning analyses, and this is really no accident. So Nilearn and scikit-learn were created by overlapping teams. Over time, their development histories have diverged a little bit, but they really were created really in the same team in the very beginning. And the goal was that Nilearn would help to bring machine learning to neuroimaging, hence the name. So for those who are, want a really nice way to interact with scikit-learn and use all the models that you've heard about so far, Nilearn is really designed to fill that gap to get your neuroimaging data into a machine learning pipeline. And over the years, its scope has expanded to include a few other things, but that's the core mission. So why would we want something like this? Well, if you've been thinking about machine learning so far this week, you may have noticed that typically what we're doing machine learning with is tabular data, right? Something where we have rows and columns. We could represent it in something like a CSV file. But if we're working with neuroimaging data, this particular formatting isn't obvious. It's not obvious how to get from neuroimaging data into this well-worn tabular format where we really know what kind of machine learning models make sense, right? And there's a bunch of reasons why this might be a little bit tricky to go from neuroimaging data to tabular data. One is that we know neuroimaging data has really complex spatial and temporal structure. So knowing where and when something was measured does tell you a lot of information about the surrounding data points. If you know a particular voxel's activity value at a particular point in a time series, it tells you a lot about maybe its neighboring voxels and also that same voxel at the next point in the time series, right? And we also know that neuroimaging data does contain neural related activity. So this is this bold blood oxygen level dependent. And here, sorry, just to state, I'm really going to focus on functional magnetic resonance imaging because this is the majority of what Nilearn is designed to deal with, is fMRI and MRI. However, there are other related libraries from the same original team that deal with other kinds of neuroimaging signals. So for example, if you're interested in EEG or MEG, M&E Python is another library which shares a lot of similarities with Nilearn, again, is really designed for this interface between those data modalities and scikit-learn, slightly different calls given the slightly different nature of the data. But I'm really going to focus on fMRI for this lecture just to keep things concrete and so we can go through some real examples. But this is a general problem, and depending on your data modality, lots and lots of ways to deal with it. Okay, so in the case of fMRI, we know that there is this neural signal related to bold data, blood oxygen level dependent data, but we also know that there are other sources of signal, or we would consider them noise maybe, because they're not really related to neuronal firing. They're related to things like head motion or some other confounds that we maybe are not as interested in modeling. And the trick is, of course, that machine learning libraries aren't designed to deal with these other sources. They aren't designed to deal with this complex temporal spatial structure. And so Nilearn really steps in to fill that gap for functional MRI data. Now, I think the goal of this tutorial, and in general, a really good thing to do when we have problems, is to just, try a couple examples, see how things go and get a sense of the data. You are, of course, welcome to replicate anything in these tutorials with your own data sets. I think the really nice thing about Nilearn is it's designed to be sort of general purpose. But Nilearn also ships with a number of data sets and atlases to try and get its examples up and running so you can play around with some data sets without necessarily having to have something on hand. And just earlier, Ariel was talking about data set showcases. I think the Nilearn ones make really, really nice, quick and handy things. I'll say that they're chosen specifically for the examples to make the examples run. So they're not necessarily the most robust depending on your particular question. Like a lot of the data sets are downsampled, for example, to 3mm isotropic resolution, just so that they run a little bit faster in the examples. But they're there, and I think they're really useful to quickly prototype things. All right, so let's prototype something. Let's go ahead and use one data set. So here we're going to use this fetch development fMRI data set. This was originally collected by Rebecca Sachs's group at MIT and hosted on Open Neuro. For Nilearn, it was preprocessed and then downsampled to preprocessed with fMRI prep, and then downsampled to 3mm isotopic resolution. And we can really see a lot about this data set from the Nilearn documentation. In particular, it has 150 children and adults, over 150 children and adults, watching a short Pixar film. So we can just download the first 30 participants. And the way that we do that is we're going to do from Nilearn import datasets, and then development dataset, fetch development fMRI. And this should just run for a second. And if my shared datasets worked, it might tell you that the dataset's already found because we have a copy locally. If it doesn't work, it'll tell you it's re-downloading it. Let's see. But yes, ideally, if we've executed this command, it knows it's on the Jupyter Hub. All right, so we have this data set, and the question is, what does it really have? So there are a couple of different things in here. We're going to load NiBabble or NeBabble, again, tomato, tomato, and we're going to actually look at some of this data. So here, if we use nibabble.load for just the first functional image in this data set, we can see its shape, which means it has a 3D structure of 50, 59, 50, and 168 volumes. Great. Okay, so this is something we didn't even really need Nilearn for, but let's actually get into the data, right? So we want to get from this neuroimaging data to our machine learning model. How are we going to do that? So one of the things that's helpful to do is just to know that we've gotten our data correctly. And the way that I like to do that is usually by plotting it. So here, Nilearn has a lot of really nice functionality to enable plotting. Here, we're going to just take the mean of that first functional run, and then we're going to plot that mean image in an interactive viewer. What you can see is you can kind of scroll around just to see the general shape of this image and confirm it looks as expected. Doesn't look like anything went horribly wrong in the loading, which is a good sanity check. All right, but we know we loaded the data correctly. We're pretty happy with it, but we know it's not tabular, which is our whole problem. So what are we going to do? All right, here's where I want the pretty formatting. So what we would like to do is extract meaningful features from the data with any kind of relevant transformations on them to deal with the spatiotemporal, structure of the signal. And one way we can do that is by what Nilearn calls the masker objects. So what are the masker objects? First, let's just think about what masking is doing in fMRI data. Here we can imagine we have some mask, some shaped however we want mask. Maybe it corresponds to a region of interest. Maybe it corresponds to a whole brain mask. And we apply it on every volume of our 4D time series. And then we're going to get back out some mask data, which is a 2D array of features by samples. And already this looks a lot more tabular, right? This is something we know a lot more about how to work with in machine learning. So masker objects basically allow us to, for a given mask or in defining a given mask, apply that mask to our time series. And we can do some operations when we apply the mask, but this is a really nice way to get directly from functional MRI data into something that we can start to move towards a machine learning model with. And of course, as I said, there are many ways to define masks. The text goes through a few in that Nilearn can create some for you, or it can take in ones that you've already defined. But that's, of course, a really big question of interest or decision point based on your question of interest. All right, so in this tutorial, we're going to assume that we just have regions of interest. We just have a mask that we already know and love. And this is going to be the multi-subject dictionary learning atlas, which was predefined in some prior work. And it defines a set of probabilistic regions of interest across the brain. So importantly, these aren't going to be the hard deterministic ROIs that you may be used to if you're thinking about masks. These are more probabilities. But I think it's really nice to showcase that Nilearn can handle all kinds of masks, right? So what we can do is run this. And then all we've done is fetch that particular atlas from Nilearn using Nilearn datasets. And then we can see some information about it. So we see it has 39 regions of interest, and they're part of a number of networks. And you may recognize some of them, like auditory, cerebellar, motor language. All right. So maybe you're not interested in multi-subject dictionary learning. Maybe you want something totally different. Nilearn does ship with a number of atlases, including, for example, the Schaefer Atlas, the Harvard-Oxford Atlas. There are also many other resources that I would point to for atlases. I think TemplateFlow is a really exciting one these days with Oscar Esteban has been working on that with many others to try and make it so it's easier to interface with many different atlases in the field. So one nice thing though is, again, just to make sure, as we did with the imaging data, we also maybe want to view the atlas to see that it corresponds to what we expect. So Nilearn provides ways to view atlases as well. Because this is a probabilistic atlas, we're just going to call plot probabilistic atlas. If it were a deterministic atlas, we would call a different function because we can handle many different kinds here. So it's going to plot it quickly. And there we go. So here it is. And now we can see this looks about right. This is about what we expect for the multi-subject dictionary learning atlas. And so, as I said before, these are our regions of interest. We're going to use a masker. Now, there's a lot of text here because there are many different kinds of nifty maskers depending on your particular regions of interest, right? So as I said, if you do probabilistic, the plotting's a bit different. The masker you're going to use is also going to be a bit different. The nice thing is that Nilearn can really handle a wide range of use cases. So if you have, for example, deterministic regions of interest, you may want to use nifty labels masker. In our case, we have probabilistic or soft regions of interest. So we're going to use nifty maps masker. But there's a full list of the masker objects, including more recent ones like the surface masker, which we'll touch on a little bit right at the end, available in the Nilearn documentation. So I would definitely point you there. If nothing else, this lecture hopefully shows you that the Nilearn documentation is near endless. And there's lots and lots of things to see there that I think are really, really helpful for running analyses. All right, so we have our functional neuroimaging data. We have our regions of interest plural from the atlas, and we have the masker that we're going to use. We can just define it using the atlas, any kind of transformations that we want to apply to the data. In this case, we'd like to do a low pass and a high pass filter and do some detrending, and we'd like to resample to the data. And then you may notice we have this .fit at the end. If you went to the lecture on scikit-learn earlier, this should look really familiar because it's the same convention as the scikit-learn estimators. We have a .fit, we have a .transform. And so we're going to conserve that same logic here to make it really easy for us to interface with these other machine learning libraries. And in this particular case, you may notice the .fit is empty. That's because we're fitting the masker to the provided ROIs rather than to our data. We're going to use it to transform our data. So let's do that. So if we transform our data using this fitted masker, just that first functional volume, we can now see that we have a new shape for our time series. So maybe this is obvious, maybe not, but effectively the data had these original dimensions, this 3D, right, dimensionality plus 168 volumes is the fourth dimension, but now it has it's two-dimensional, where it's 168 by 39. And so this is a really good point whenever you're working with machine learning, just to make sure your dimensions add up. This is always, I think, one of the core things that get people. But what happened here, right? So rather than providing information on every voxel within our original 3D grid, we're only considering voxels that fall in our 39 regions of interest from our atlas that we've defined. And so within every region of interest, individual region of interest, we're aggregating information from all the voxels using that probabilistic assignment of the soft multi-subject dictionary learning mapping. And then we now have this 39, which is reduced from our original 3D dimensionality for our 39 provided ROIs, but we've kept the 168, which is our fourth dimension for time. Now it's the first dimension. So what happened? Basically, we reduced the dimensionality spatially, and we flipped our two dimensions of time and space. And the reason that we've done this is, again, for compatibility with scikit-learn, because in scikit-learn, the convention is that rows in a matrix are samples and columns in a matrix are features. So this is a really nice illustration from Jake Vanderplas's Python Data Science Handbook, and you can really just see this laid out. But now, of course, what we're doing is basically saying our features are each of our ROIs, and our samples are every time point that we have access to. And so we've needed to flip this to match this convention. And this is something where if you're trying to do it on your own, it's easy to forget this flip. And so a nice thing about working with Nilearn is that it will impose this convention for you, so you don't accidentally end up with flip dimension when you're working with scikit-learn estimators. Awesome. Okay, so what can we do now that we have this data? We could go straight to a machine learning model, but often with neuroimaging data, it isn't necessarily interesting to look at the time series within ROIs themselves. Maybe we want to do something like creating a connectome, right? And so with Nilearn, we can really easily estimate functional connectivity as pairwise correlations between ROIs using this connectivity measure estimator. And what's nice is we can tell it what kind of functional connectivity we'd like to estimate. Here we'll say correlation. So we're going to define this estimator. We're going to fit transform all of the ROI time series that we generated just here when we used our masker to transform our functional neuroimaging data set. Or in this case, excuse me, yeah, we're going to take the first. And then we can just plot this functional connectivity matrix. So if we plot it, I'm going to fill the diagonal with 0 so it doesn't overwhelm, because it's definitely going to be the highest correlation of a thing with itself. But you can see something that really looks like a functional connectivity matrix with a strong structure. So here, for example, you can see these blocks along the diagonal, as well as some anti-correlation off diagonal. And so this is something that maybe looks a little more familiar to us as neuroimagers, and also is a really good starting point for machine learning. But because we can, just want to make sure things make sense, Nilearn provides many different ways to view this information. So we can also view it as an interactive connectome using just the plotting view connectome of the correlation matrix. And we can actually see what it looks like interactively, which is really helpful. Now, one other thing that you might want to be aware of when you're doing your imaging data. So you may think, great, okay, I've extracted the data. I went ahead and I created connectivity matrices, and now I could just take these connectivity matrices and go and do machine learning with them. But I believe it was said just earlier today that, one of the things that makes working with biological data, neuroimaging data, so challenging and important is that we need to be really thoughtful about the kinds of transformations we apply to this data. So as we started with, in our case, fMRI data isn't pure neural activity. There's also various noise sources in it. And we can really easily trick ourselves into learning from noise if we're not careful. So one thing we can do is try and account for some of these noise sources, at least the ones that we are aware of. In this case, this developmental data set also includes a confounds attribute, which was generated during the fMRI preprocessing. And we can just view it and see that this may look familiar. We've got our translation parameters, our rotation parameters, framewise displacement, comp cores. So this is all information that's really, really useful to know about the kinds of noise that were present in the original fMRI signal. Now, I'll note this is actually a subset of all possible fMRI prep generated confounds. And you can control exactly what confounds you'd like to get for this particular data set. But here, if we just revisit our exact same example we walked through above, but let's just do it a little faster because we've seen it once. We can transform our dataset time series as we did with the multi-subject dictionary learning ROIs. But now we're going to pass the confounds to that particular estimator. And then we can go ahead and use that corrected accounting for confound time series to generate a corrected correlation matrix. And we can plot that again. And now we see the pattern of connectivity looks really quite different. So I'll just load one on the left and one on the right. This is when we, this is when we didn't account. And then this is when we do account, right? And so now we can see that by accounting for confounds, we get a very different pattern of functional connectivity, which is really, really important to know if we're going to go take this and bring it to a machine learning model. And as before, just to show that you can do this as well, we're going to view the functional connectivity matrix as an interactive connectome using Plotly. In this case, again, called through Nilearn with this view connectome. All right. So in general, we see that in both the matrix and the connectome forms, there's a really big difference, but we're much closer now to being able to actually do machine learning with this neuroimaging data, which is pretty exciting. So I'm ready to step into actually doing an example classification problem, but I want to leave space just to see what questions people have, if any, at this point. No? Okay.
I'm curious.
Oh, yeah.
Sorry, you specified like the option, I think, and you made it a correlation within the code.
Yes.
And I was wondering if there's like a command that we can use to see what options exist.
Yes. Okay. So the question was, is there a command you can use to see what options exist? So it's funny you talked about that particular option because we're going to go through it a lot in the next thing. But in general, you can refer to the function documentation, or in this case, let's say from Nilearn, import datasets, datasets.fetch Haxby. That's datasets.fetch Haxby. This is a different call that we will do later. If I put a single question mark in IPython, it'll just give me the doc string, and the doc string should tell you all the information about each option or each parameter and what its options are. And you can see what it returns. In fact, IPython's really cool because if you do 2 question marks, it'll not only give you the doc string, it'll actually go through and give you the source code of the function. So you can really see exactly what it's doing. That's the way to get it from the terminal. That's the way I usually get it from the terminal. But the other option, of course, is to go to the documentation website of the particular library and see what their, usually it's called an API documentation, what their API documentation looks like. And in this case, we go to connectivity measure and we can see for kind, covariance correlation, etc. Exactly as we would have seen in IPython if we did the question mark, but just rendered on a website. Pretty. But great question. Any other questions that people have at this point?
What if we have surface data? Can we also get the ROI time series?
Yes, that's a great question, because that's new. And one of the reasons we're updating Nilearn to be 0.12.0 is now, this is quite a bit later in the example, so I'll just quickly show you here. But now we have surface maskers. So we're now able to treat surface data as sort of a first class data type in Nilearn, and extract, much as the same routine as we did in the volume, extract things on the surface. So it's not, it's not, I would say, as comprehensive of support for surfaces yet as it is for volumes, because this is something we've been iterating on, but it is now there. So you can do almost everything I showed you today so far, you can do in the surface as you can in the volume. Yes. Awesome. Okay. For time, I'm going to keep going, but please, again, don't hesitate to shout. All right. So let's go ahead. We're going to go faster. We're going to sub-select based on time. That's how I'll describe what we're going to do. So, all right. We have a connectome now for an individual subject. This is great. And we really understand what we're doing, which is really important. So now what we can do is just scale it up. Rather than just doing it for one subject, let's do it for all 30 subjects that we had fetched previously. And in this case, we're going to keep the connectivity measure at correlation just to show. It's taking just a second. So I'll show you over here. But basically, we are doing the same thing. We download the data, we download the atlas, we set our masker and we set our connectivity measure. And now we're going to loop through all 30 participants and we're going to extract their relevant pieces of information. So we're going to use the masker to transform their functional file into a time series. And we're going to append that time series either to a child or an adult group based on their phenotypic information, because for every participant in this particular data set, we know, were they children or were they adults when they were scanned? It's really thinking about it. Okay. Let's just keep going here. Now, just because we scaled up and we did it more quickly doesn't mean anything's changed. If we take one of those extracted subject time series, it has exactly the same shape as we saw in the last notebook, right? So it still has 168 time points by 39 ROIs. So the basic premise is exactly the same. The only thing that's different is we did it in this for loop. So we can do exactly what we did previously. We can now create the functional connectomes, but we can create functional connectomes for the groups rather than just for each participant one by one. So correlation measures expects a list of time series. So we're going to supply the list of ROI time series we just created, again, in that for loop. And it will then be quite clever for us and compute individual correlation matrices for each participant in the list. So in this case, because they're children and adults, let's split it out like that. We're first going to look just at 24 of the children, because that's what we have in this particular sample. And we can take those correlation matrices. We can take those correlation matrices and stack them. And so when we stack them, we now see we have 24 for the children and 39 by 39 for the correlation matrices. From there, we can also do some really nice things using this particular connectivity estimator. It makes things a bit easier for you. You can, for example, get the mean across all fitted subjects using the mean attribute, the average correlation. And that's just going to be a single functional connectivity matrix. But we can also plot any of the functional connectivity matrices just as we did earlier. So this is child 0, child 1, and child 2. And here we're showing that mean connectome over all 24 children. Again, using this interactive viewer with plot view connectome. Just try restarting that. Awesome. So the question earlier, one of the questions earlier was what are the options for connectivity measure? So here we're going to experiment, and we'll see that rather than just doing correlation, we can try some of the others. We can do partial correlation, for example. Interesting. Okay. And we just fit that by passing kind as partial correlation. And then when we view this, we see right away that the partial correlation or the direct connection connectome, so this is each edge taking into account all other edges, each pairwise connection taking into account all other pairwise connections, are weaker than the full connectomes for the first 3 children, just based on the fact that we have the same color bar. And if we do the mean partial correlation connectome exactly as we did before, you can again see this is much weaker than our previous one. Another option we can try, rather than partial correlation connectomes, because people often consider those to be quite conservative. So maybe instead of taking into account every single other connection, we want to do something a bit different, is to use the tangent space embedding, which basically takes both correlations, and partial correlations to capture reproducible patterns at the group level. So this is really a group kind of analysis. The structure is exactly the same as before. We pass kind as tangent, fit transform all the children, and now we see something a bit in between in terms of the relative strength of the connectomes. But it is much harder now to interpret these. For example, the mean connectome is really designed to be 0 in this particular modeling approach. And so we can't view or interpret the mean connectome. We're really interpreting every individual participant connectome as deviations off of that mean connectome. All right, so what we've done could be considered so far in machine learning as feature extraction, right? We've figured out how to go from our neuroimaging data to all the way to connectomes of different kinds. And now we can really ask, all right, we have these features, let's do some machine learning. So what we're going to do for that is import scikit-learn, which you've seen earlier, and the whole benefit is this is super fluid to interact with Nilearn. So we import a few functions from scikit-learn. In particular, what we're going to try and do is a classification analysis. So we're going to import accuracy score, which is how we'll judge the classification analysis, stratified shuffle split, which is how we'll split into our training and testing set, and linear SVC, linear support vector classification, which is how we'll classify. And in this case, what we're going to try and classify is whether or not these participants were children or adults when they were scanned. So here what we're doing is we're taking various kinds of connectivity measures, the 3 that we've tried so far, and we're going to say, okay, we have these groups, which are whether or not they were children or adults, and we want to use this information to split, well, to create a CV of a particular size, and then basically just go through this really small loop and do everything that we did. First, we're going to take our pooled subjects. So this is just the ROI time series, and our classes, which tell us children or adults. We're going to generate connectivity measures of a particular kind. Again, this is correlation, partial correlation, tangent. We're going to use those connectivity measures to get connectomes for our training subjects. Then we're going to classify for our training subjects those connectomes. And then we make predictions for our test subjects using this classifier predict, again, using their connectivity features. And then we store the accuracy for a given cross-validation fold. So it rolls together a bunch of things you've seen here and in previous machine learning lectures. to say, we need a training and a testing set. We need to do feature extraction, in our case now for neuroimaging data. And then we're going to go ahead and classify based on our training set and predict on our testing set. And then we need a way to say, how well did we do? In this case, we're going to use the accuracy score for our testing set. And now what's really cool is we can take this really short loop and use it to display the results. So how accurate are we in figuring out just from their functional connectomes if a particular participant was a child or an adult? The success varies depending on the particular kind of connectivity measure you use, is what we find. So, for example, if you use partial correlation, we see that we're basically at chance accuracy. And in this case, there was an unequal distribution of children and adults, which is why we see chances is not at 50-50. But we see partial correlation basically has chance accuracy. Correlation is higher, but still the confidence interval is overlapping with chance, whereas tangent space embedding is doing significantly better than the other two methods in helping us classify, is this a child or is this an adult participant? So this is a really small, quick example, but I think it does a really good job of showing, understanding our features for neuroimaging can really make a big difference in our machine learning pipelines. So I think this is a really nice way to start to appreciate what Nilearn can do in helping us to bridge that gap between neuroimaging data and machine learning. All right. Don't know what that was. So let's go ahead. There's two other things I want to show you in the 15 or so minutes we have left for actual hardcore lecture time, but there's lots of time for questions. So what questions do people have on this last section on our first real classification problem with neuroimaging data? No? Okay. Then we can keep going. Awesome. Yeah, I'm not sure how these marks happened on the hub, but maybe
I think someone annotated the screen.
Ah, okay. I was trying to figure that out. That makes more sense.
Yeah.
Unfortunately,
All
I
right.
can only use those two.
Can I erase? Can I clear? Clear all drawings. Boom. Look at that. 21st century technology. Okay, cool. I'm glad other people were also a little confused. All right, so we've done classification with a really small example, but I think this is one of those things where as we start to think about machine learning models, we often have more questions than answers, right? So we have this particular model that we've just run and we're like, this is great, I think, it's better than chance, but it's just one sample of 30 participants. How robust is this classification really? What have I really learned, right? And so, we thought a lot about feature engineering in terms of choosing the right kind of connectivity matrix, in terms of choosing our atlas, in terms of including confounds, and the question, of course, is which ones to include. But there are other questions that are really important to think about the model that we use or the model that we train to generate our predictions and how we're going to assess the generalizability of our learned model. And in this example, I just want to quickly touch on, although I think it's a much longer example that we could talk about in a lot more detail, the importance of appropriate cross-validation. So if we look at a recent reviews showing common cross-validation methods in neuroimaging from 2017 to 2019, so not as recent anymore, but still I think quite informative, you can see that the majority of studies in this particular sample didn't use any cross-validation at all. Which is, I hope at this point, pretty obvious, not something that we are not interested in doing if we can avoid that. Other common methods include k-fold or leave one out or leave X out. And this is really often driven by the fact that our sample sizes historically have been very, very low. for these kind of between subject analyses. And so what we're going to do is touch on why cross-validation is important, and we're going to stick with the developmental fMRI data set because we pulled 30 subjects from that data set. But in fact, as I said at the beginning, this is a slightly larger data set with about 150 participants. So in this bar, so not as large as many data sets that we see nowadays, but still, I think, useful to make some of these points. All right, and one thing that's been said previously, as I heard it in a lecture, but just to really emphasize, best practice is always going to be to have a separate held out validation set if you have enough data. This is really what's going to make the difference between being able to really utilize your training set and having to be really quite careful about how you deal with your train and test split. All right, so what we can think about this in a couple of different ways. For the sake of time, I'm not going to go through too much of the formalism. I would encourage you to spend some time with this if you're interested or if you have time. But basically, there's two important take-homes. One is that our evaluation procedures really need to test predictions of the model on held out data, right? So this is why cross-validation is important in general, is if we look at the model, what we train on is not going to be informative for how the model performs compared to what we test on. And cross-validation procedures that repeat the train test split many, many times to vary the training set also help us to ask some interesting related questions, like given future data to train a model, a machine learning model on neuroimaging data on a clinical problem, what's the error that I can expect on new data? So I think, rather than just doing one train and one test, ideally varying the train test splits and super ideally having a separate held out validation allows us to make much stronger inferences about our prediction than just learning on a particular training sample. And we've already seen that it's very possible to do this just in those 30 participants we did in the last example, right? We varied the train test split. All right, so there are many different forms of cross-validation in machine learning. Scikit-learn is another beautiful documentation website. If this whole tutorial is an example of how powerful the Nilearn documentation is, because a lot of this material is from the Nilearn documentation. The Nilearn documentation is a testament to the Scikit-learn documentation. There's literally a course now, a MOOC on Scikit-learn, which teaches from this. So this is really, really useful stuff. And there's a section there just on the importance of cross-validation in machine learning and the different schemes that exist. It's absolutely worth reading through. But in our case, as we started with, what's fun is to just try things out in our example. So this time, the main difference from what we did previously is we're going to fetch all 155 participants, so we don't pass n subjects. We keep the same ROIs. We keep the same masker. We keep the same connectivity measure estimator. In this case, we're just going to decide on correlation, not because it performed the best. In the last example, as we saw, it really was sort of middle of the pack, but it's the most commonly used. And now we're going to do the same for loop that we did before, where we extract using that masker, the time series for each participant. Yes, okay. And if you did not update your Nilearn, you would see this error. So let's just go ahead and restart it. Awesome. So while that runs, I'm just going to do the cooking show thing of showing you what it looks like, because it takes about 4 minutes. So in this case, we have exactly the same cross-validation scheme that we did in the last example of stratified, shuffled, split, stratifying by group, shuffle splitting the data. And now what we're going to see is that we can, for the train test split, calculate again our accuracy scores. And we get our stratified shuffle split, accuracy. we're going to just print the mean of all of those scores and the standard deviation. And we see that it's really quite high. So 0.95 plus or minus 2. And one nice thing that we're going to use here is from scikit-learn, we can actually import this confusion matrix display. So this shows us where the model got confused in its classification of groups. We can see that the true label was mispredicted once, but in this case, and then, yeah, basically, we can see that we are usually predicting the right thing on the diagonal, but we are getting confused some of the time. And I see I had a question, sorry, in Slack. So quick clarification, which goes back to chance level. The chance level should account for the size of the groups and not just be binary. That's a great question. Yes. So the question is basically, when we assert what chance is, there are only 2 classes, but in these particular samples, each class does not appear an equal number of times. So it's not as if our sample has an equal number of children and adults. In fact, it's very imbalanced is the term really. It's much more children than adults. And you can actually see that in the confusion matrix. We're much better at predicting children than we are at predicting adults. So yes, when you calculate chance level, you don't just want to be thinking about class, the number of classes you have. You want to actually be thinking about, in this particular sample, what's the distribution of classes that you have. And you know, when you do your cross-validation, there are, as I said, many different schemes, but given the amount of imbalance you have, there's many different ways to account for that and move your chance or to move your classification sensitivity. I believe Guillaume Lemaitre just got this merged into scikit-learn a few months ago from scikit-imbalance to try and have new ways to tweak your classifier. So imbalance is a big thing. You do want to be thinking about it when you're looking at your accuracy. Awesome. Okay, so one other thing I want to show you, speaking of imbalance, is what if we just pretend that we have an equal amount of children and adults, right? So here we are stratifying by group, and we're still, you know, we're still mostly predicting the majority class right. We are predicting the majority class right. The class where we have less data, we're predicting right most of the time. Sometimes we make some mistakes. What if we say, you know what, I'm going to forget about the fact that this data is imbalanced. I'm just going to put it all in and have it predict, see what the model does. In this case, we just use k-fold, which is going to totally ignore the group identity when it does the cross-validation split. And we see that our accuracy has dropped. We may say, that's really odd. You know, we had really good accuracy before. Why is it so low? Well, the reason it's so low is because now it's only predicting one class. It's only predicting the majority class. So it says, I think everyone is the same thing because that is what I've seen the most. And so in this case, it happens to be that we have enough adults, which are the minority class, that this is dragging down our accuracy. But this is absolutely something that in a real data set, you can easily confuse yourself by if you're not tracking the relative proportion of your different classes. So imbalancing is really important, and it's definitely something to pay attention to. I also want to bring up, and this is something I believe was touched on already in the scikit-learn lecture, but here we've just been using accuracy. This is a limited metric in some ways. There are many other metrics that are useful, such as the receiver operator characteristic. So we can use scikit-learn to really get all of this really smoothly with Nilearn in the pipeline. So here we can see our ROC curve. We can try and interpret it a little bit. And then we can actually look at the variability over different cross-validation folds. And finally, super relevant to neuroimaging on this example, the one thing I wanted to make sure you hear from this is that with smaller sample sizes, we're just going to see a wider distribution of errors, right? So if we look across the literature, we can see that different methods of cross-validation are employed many times because we have relatively small sample sizes. And so if you have a small sample size, let's say three subjects, excuse me, You leave one subject out, that's a whole third of your data set. So the errors you'll see are going to be much wider than if you have 300 subjects and you leave one subject out, right? And so when you're thinking about how to do cross-validation, the relative sample size that you have available is going to be important. So if we take, just to get a handle of this in our development fMRI data set, if we take the whole 155 and we start systematically subsetting it, right? So we can just repeat exactly the same procedure that we had before, but first we're going to go just to 15 participants. Remember when we used 155, we were at 0.95, I believe. So now we're at 15 participants, then to 5 participants. And we see that, you know, the accuracy is now the same, but the error, the standard deviation is increased. And then if we compare the distributions of these accuracy scores for each cross-validation scheme, what we see is basically before, when we were using 30 in our test set, it was a much more concise distribution. Now with 15 and then with 5, we can see that the distribution of errors is very, very different, very much wider in the smaller case. And so when we're trying to make inferences, you know, having more data is always better, but given the amount of data that you have, that will give you slightly more information about what kind of distribution of errors you should expect. And if you don't see that, that's a good reason to look into your model. Because, for example, one thing that commonly happens is you might actually have some kind of data leakage between your train and test. Awesome. Okay. Ariel, do I have like 5 more minutes, or should we call for questions?
You have 30 more minutes.
Perfect. Then we're good. Okay. Amazing. Great. So let's, before we switch gears to the general linear model, which I know everyone loves, let's stay on machine learning for a minute. What questions do people have about machine learning that we've touched on so far, on classification, on cross-validation, on just getting neuroimaging, functional neuroimaging data into this pipeline?
Are you able to hear me?
A little bit. You're faint, but I can hear you.
Okay. My question is, earlier it said when we're using the mask,
Yeah.
there's an option of using like clustering, like union clustering or something like that. And so I have 2 questions. One, is there an example of doing that with Nilearn? And then also, what are the advantages and disadvantages of using like a clustering algorithm as opposed to a atlas?
Sorry, I missed the very last word. A clustering algorithm as opposed to what? Sorry?
As opposed to an atlas.
An atlas. Thank you. Okay. Yeah. So the question, as I heard it, please correct me, is, you know, there's different ways that we can divide data to use in a masker. In Nilearn, we could do clustering with Nilearn itself, or we could do a predefined atlas. And so 1, are there examples? Yes, let me pull some up. But then 2, what are the advantages and disadvantages? So first, hopefully I got that right. First, let's just show some examples. So if we go and we want to do clustering, what's the best way to do that? Here we go. So here's an example where we can do this, right? Basically, we can take these parcellations class. So it's in nilearn.regions.parcellations. And we can use that to do multiple different kinds of clustering. We could do, for example, ward agglomerative clustering, which is a bit more hierarchical. We can do k-means clustering. And basically the idea is that you can see when you do clusters that you get very different kinds of boundaries than you would maybe see in a particular atlas. So the question is, why would you do one versus the other? I think this is a great question. It really depends on your questions and your data. So I will say that a lot of what we call atlases nowadays have been defined in many, many different ways. of course. Some have been defined using more anatomical definitions, but many have been defined using effectively clustering algorithms on a reference data set. So the idea was basically that they had a really high quality data set they were going to learn a particular parcellation on, and that was going to be what served as the reference for other people. You'll see this a lot. So for example, if we go and we look in the API, we can see data sets, we can see atlases. So for example, I can tell you this idea of learning a parcellation and then using it as an atlas happened for Basque. It happened for Schaefer, certainly. It happened for Yo. And for the probabilistic, it's perhaps even more common. It happened for Craddock, for DeFumo, and MSDL is, of course, another example, actually, where they did dictionary learning, which is a kind of parcellation method, effectively, you can think of, and then used it on a reference data set to define an atlas. So really, I would say that there's a lot more similarity than differences. The difference primarily is that an atlas is a predefined definition of the brain into different regions or parcels that is already recognized in the community, and that people are going to know how to interpret. If you do your own parcellation, there's a lot more to be thought about or to be explored in terms of, okay, why did you choose this particular parcellation? What information is it telling you about your data set uniquely that maybe a pre-existing atlas wouldn't tell you about your data set? So long story short, it depends, as all things do. But there's nothing wrong necessarily with either approach. I wouldn't say one is distinctly better than the other. I'm trying to think. For example, maybe I'll give an example. In my own work, I do a lot of this idea of functional alignment. So basically, it's a domain adaptation approach where you're trying to say, I want to make some data look more like other data. And to do that, many of the methods require to work in small regions, but I don't have any particularly strong reason to use a given atlas. Instead, I'm going to learn from the data what those regions should be, and then learn the transformations within the parcellation that I've learned. In other cases, maybe I want to make inferences in particular regions of interest and map them out to the literature. And in those cases, I would use an atlas that someone else defined that I found has been really, really helpful for conceptualizing activation in particular regions that are linked to, in my case, maybe something like movie watching. Really good questions. What other questions? Yes.
So could we dig into more how to make the mask? It was really quick. So let's say.
Yeah, absolutely. So the question was revisit how to make a masker. Is that right? Yeah. Okay, perfect. So yes, it was really quick because there's so many different ways, and I cannot cover all of them, but it's great in that hopefully I've excited you to go look at the Nilearn documentation. But basically, what we're going to do is when we actually instantiate the masker, it's really as simple as calling from Nilearn import maskers, masker dot whatever particular masker you have. So in our case, in this example, we had probabilistic atlases, so we did a nifty maps masker. But if we were to go, let me just show you what I mean. If we were to go to maskers, we can see that there's many different kinds. So there's a nifty masker. This is typically where you have just a single region of interest or a whole brain mask. A multi-nifty masker, you have multiple subjects or multiple runs, and you want to apply the same singular mask to all of them. Nifty labels masker, this is the deterministic or hard parcellation boundaries. Nifty multi-nifty labels masker, multiple subjects, same idea, hard deterministic parcellation boundaries. Maps masker, that's what we're using in this example. So that's probabilistic. As you may have guessed, there's also a multi-nifty of the same one for multiple subjects. And then we have a few others. So we have a spheres masker. This is where you're just providing a particular coordinate in the brain. You say, I know I want activation centered on this particular coordinate, and I would like a sphere around it, and I would set what the radius is. That's a masker that allows you to do that. A surface labels masker allows you to say, I have a surface image, as I promised. These are now moving towards first-class citizens. So I have a surface image, and I would like to extract data within particular atlas regions, just as I did for labels masker. So again, these are deterministic. And then a surface maps masker, probabilistic, but on the surface. And a surface masker is analogous to nifty masker. So that's the whole zoo, which is why it's hard to go through all of them in as much detail. But the nice thing is there are many different ones for your particular use case. When you decide the one you want to use, all you really do is from Nilearn import maskers and then maskers dot the particular one you want to use. And then you can pass various things. So in this case, if we go and we look at Nifty Maps Masker, ooh, where did I? Here we go. We can see that it has many, many different options, which is maybe the other thing that you may have noticed is that we have a subset of options passed. So basically, the whole premise is that just as we said before, the goal is to take our neuroimaging data and get it to something that we can start to do machine learning with. And because we know that our neuroimaging data has both neural and non-neural noise, the Nifty maskers broadly want to make it as easy as possible for you to account for this noise. So for example, you can do things like pass a smoothing kernel directly in the masker, and that will smooth your data for you as it extracts it. You can also do things as we had done, like pass a high pass or a low pass filter. You can pass standardization. You can extract high variance confounds, which is kind of analogous to T-comp core, but Nilearn will do it for you directly. So these are all different things that the masker will try and handle for you, such that you can go straight from your neuroimaging data to something that you would like to do machine learning with, or to connectivity measure in our case. But hopefully that's a little bit clearer in terms of how to orient to what the maskers are, because there are a lot of them. So it's hard to do it step by step. I would say the best thing to do is just take these examples, and instead of doing the multi-subject dictionary learning, what I would recommend is to really go back to you go to the API, go to data sets, you go to atlases, just choose some different atlases. So choose a deterministic atlas and try it with Nifty labels masker. Choose a particular coordinate and try it with Nifty spheres masker, and see how the code changes, because really it should be just as simple as changing the particular masker object that you're doing and changing the particular atlas or regions that you're putting in. And you can see how that leads to all the changes downstream. But it's a great question.
Thank you.
I see a different hand. I see two hands.
I'm particularly interested in whole brain analysis and in the kind of component analysis in particular. And what I was thinking is, I see that you have here the SNAP atlas for ICA, which is really interesting, but sometimes I notice that like my components can actually include areas that are, for example, part of the cerebral network. And I'm not entirely sure that like I couldn't actually remember if we have that network included in that. So what are your thoughts of having multiple atlas thing, like at least to compensate for those areas that are not showing up in one of the atlases, and I want them to be included in my atlases for comparisons for example.
So sorry, I think it dropped out just a little bit. So the question is, what are the thoughts on including multiple atlases? And the motivation is because I missed that part. You have some atlases that.
Where they're composing the signal, some of my components can actually be part of a network that's not included on the atlas that I select, and I like to include those components in my analysis.
Okay, I think I heard it, but please correct me if I'm wrong. Yeah, so I think the question is basically, you may have some atlases that correspond to a particular network or a particular question. You may have other atlases that don't. What are the thoughts on using multiple atlases? So in general, I would say that using multiple atlases can be a really good thing. In the machine learning literature, this is commonly known as bagging. It's a different way of like doing bootstrap aggregation. So we've done this a couple of times where basically you use different atlases to extract different features, and then you use that as a form of bootstrapping over your sample to try and get a more reliable estimate of whatever it is you're actually interested in. So for example, you could imagine, it's a bit hard to imagine in the connectome case, but you could certainly imagine some other cases where you're extracting values from regions of interest, and you're going to aggregate over multiple different atlases to try and bootstrap from the data multiple different kinds of features, and then test, does that bagging procedure improve the reliability of your estimates? I think that's something that's really, really nice, actually, and has been explored somewhat, but I think should definitely be explored more often with many of our neuroimaging questions. The other piece that you maybe touched on that I'll just say about atlases is if one of the motivations for doing something like multiple atlases is that some atlases have coverage and others don't of a particular region that you're interested in, I think this is something that we at Nilearn have been trying to highlight a little bit more, but is really important for people to realize when they're doing atlases. Commonly, particularly if we're taking atlases that are published in the field and just applying them to our data sets, people may or may not realize that the coverage doesn't always totally overlap between the atlas definition and your particular brain volume. So this is something we try and account for as best we can in terms of the resampling, but sometimes the data just isn't there. And so checking that overlap between your atlas and your data. So here we're doing something where we're just plotting it on the MNI, but we could also really plot it on our functional and look at that. I think that's really hugely helpful for making a decision about which atlases to include. Because if an atlas doesn't have a lot of information in your regions of interest, or you don't have a particular parcel filled in, maybe given your particular scanning sequence, then that atlas isn't as useful to you. And maybe something like bootstrap aggregation can help, but making sure that you have really high quality atlases going in is going to make the results that you get out a lot better. So I would just say that checking your correspondence between your atlas and your field of view or your particular scanning acquisition is another thing that I would absolutely look at when choosing atlases.
Hello, I'm the other hand that appeared. I'm just wondering if you have any, I wanted to ask if Nilearn includes any kind of feature normalization functions. I'm currently struggling quite a lot in a machine learning project to decide how to standardize my features in a way that kind of keeps some kind of biological possibility of like relationships between ROIs, but it also standardized in a way that my machine learning model likes the way the distributions work. So I was wondering if Nilearn incorporates any of these kind of functions to standardize or normalize your imaging data, or if you have any thoughts on it.
Yeah, this is a great question. This one dropped out less, so hopefully I got it correct, but please let me know if I didn't. So the question is basically, machine learning models are often very sensitive to scaling. This is a known property where if data are scaled differently, many different kinds of algorithms will really pick up on this scaling rather than on our particular features of interest. So, to feature engineering for neuroimaging data, it's really important for neuroimaging data and as well as for, basically any other kind of data source that you're going to get to think about scaling. So Nilearn does think about this, and we've tried to help with it in various ways. So for example, in the maskers, we don't enforce standardizing because people may do it in different stages of the pipeline or anywhere else, but we do provide mechanisms to standardize, and we provide different ways. For example, you can z-score the sample, you can z-score where you're shifting to the population standard deviation rather than the sample standard deviation. You can do percent signal change, or you could do a simple true or false. True is the same as z-score, really, and false is just the default, which is don't standardize the data. So this is one of the ways that Nilearn has built in this idea of trying to help standardize. You can also standardize the confounds that you pass in, because this, depending on your particular correction method that you've chosen, this may make a difference. You can also choose whether or not to detrend the signals. This is a related idea about trying to get the signals such that they're in a more similar amplitude range before standardization. So there's lots and lots of ways to do this. I think it is really important for many algorithms, as you pointed out, and Nilearn does try and make it possible. We don't enforce a particular convention because, again, it does kind of depend on your exact pipeline and what algorithms you're going to use, but it is all, batteries included if you want to do this with Nilearn. Absolutely. Awesome. All right. Okay. We have a few minutes left. So we'll just go through one last example. 1 point, really like a half example. Because I want to show you the other side of Nilearn. So Nilearn, as the title suggests, was really originally designed to do machine learning with neuroimaging data. But back in 2019 or so, the decision was made to expand Nilearn to include what at the time was known as NiStats. So now Nilearn officially does machine learning and statistical analysis. And these two can come together in really quite nice ways. So what I want to show you at a high level, given the time, is that you can do a general linear model that you would do in many other packages. You can also do that in Nilearn. And in fact, that can be a really useful thing to do for machine learning. So to show you this, I'm going to point out the existence of a different data set, the HAXB data set. I heard earlier there are a lot of visual neuroscientists in the room, so maybe you're familiar with this. This is a canonical data set from 2001 that was really pretty influential at the time. And the idea was to investigate the differences between face and object processing in ventral visual stream. So, this is the description of the data set from Nilearn, which I would encourage you to look through. And there's, here it is here, just slightly longer. All right, so this data, I'm going to go through this part a little bit quickly because this is all very similar to what you've seen before in the development data set. I'm just showing you how it exists in HAXB data set. So this data does have functional data, and we can see this is the mean image for it. And it looks, like reasonable whole brain functional data. We can also see, though, unlike the developmental data set, for this particular data set, we have access to the stimuli that were shown in the scanner, and we also have access to the timing information of those stimuli. So the design of the experiment was that there were a number of different visual categories, 8 presented visual categories, plus some rest sequences. So if we look, we can actually get stimuli from, this one's flipped, from the different visual categories. Here we go. So you can see shoes, scissors, houses, faces, scrambled pictures, which were controls, chairs, cats, and bottles. And so these were the kinds of stimuli that people were actually viewing in the scanner. And one thing that's nice is we have these accompanying files. In addition to the functional data, we have these called session target files, which are the CSV files, which tell us the presentation of each image and its particular category, right? So the CSV files look like this. This was way before the invention of BIDS, so they are certainly not BIDS compatible, but we can still use them. So there are two columns here. There's labels and chunks. Labels is going to tell us the visual category or rest, and chunks is going to tell us the particular run, because in this case, all the different runs have been zipped together into a single Nifty file. And so what we can do is see the unique visual conditions, see the unique runs, and we can infer the structure of the run and what happened for each event. So what we can do with that structure is fit a general linear model. Again, given time, I won't go into the formalism, but I would definitely encourage you to review this. And there are many, many good examples walking through, what is a general linear model actually fitting. But what we're going to need to do for Nilearn's purposes is create our X matrix, our design matrices, because that's going to tell the model what happened and when. So what we can do is for each of the unique runs, we can split that data out. We can look at how many scans were in that run, what stimuli were presented in that run, and what time those stimuli were presented. And we can see that the result will look something like this. So we know at 15 seconds, a scissors stimulus was presented and it was on screen for 2.5 seconds. So these are all unjittered. Each stimulus presentation is tied to the TR. What's nice is that Nilearn provides us some functionality to take this really minimal timing information and make a design matrix. So we can really easily get something that tells us, okay, not only do I want to include my timing information for my different events, I also want to include, in this case, for example, some drift terms, my constant, that's really important. In general, I would encourage you to include confounds in here, much as we saw with the fMRI prep ones. But again, this data set was published in 2001, so we don't have access to the full suite of things that we might want. It's still really nice to illustrate the concepts, though. So what we're going to do is we have this timing information, which we basically just took from the included CSV and reformatted. And I showed you this design matrix because it's nice to see and think about. But for Nilearn's purposes, what we can do is actually just import an estimator called first level model from GLM. And this is going to allow us, this class, this module GLM, is going to allow us to fit things like first level models, as I'll show you in this example. It also allows us to fit second level models, and it allows us to do lots of really nice things like cluster correction and things I won't have time for today. But once we import first level model, we can just use this estimator to fit in the same scikit-learn convention our GLM. So we can instantiate the GLM with a brain mask that was provided with the data set and with some information. So we know the TR from the original publication. We can also choose a high pass filter, choose a smoothing filter. And then we can just loop through our data set. So in this case, we're just going to loop through that one participant because we're going to keep it first level model. We're going to do it within participant, but we're going to extract the different chunks, they called it, or runs from that one Nifty file. For each chunk or for each run, we're going to fit, same scikit-learn convention, the GLM, using that minimal timing information I showed you earlier. And then we're going to compute a contrast. So this is going to say, for this particular visual category, what is the map that I get for this run? And we're just going to save those statistical maps. What's really cool, one of the things I wanted to show you is that in the newer versions of Nilearn, you can actually then get a report for this GLM, which will tell you all kinds of really useful things. So you can save it, you can view it in a notebook, but it basically tells you, okay, this was the version of Nilearn that was used. We ran this at a subject level. Here were the particular parameters that we passed to the first level model. Here were the regressors. And then, here's the table value of the parameters. Here's that design matrix we saw earlier. It's already computed for you and included in the report. You can get a correlation matrix between all your regressors. You can see the actual contrast you estimated, and then the brain mask, and then the statistical maps, which again are going to be quite noisy because this is just within participant over a number of runs. But this is all computed for you here, and each one will have a calculated cluster table where you can see the peak statistic and the cluster size of that particular cluster. So all of that can be generated really easily just from fitting the GLM and then glm.generate report. Now, I definitely won't have time to show you this, but I just want to hint towards you can do all of that and then take those generated statistical maps and actually do what we did in the beginning, a classification analysis. You can take them and try and do a classification analysis to say, okay, now rather than having children and adult as my groups, I can have different run labels as my groups. And can I correctly predict which visual category this was from its map? And you can see that indeed you can get pretty good classification accuracy from this. And if you want to view the results for the coefficient image, you can do that on the surface, and you can get another little report to show it. So that is a very high-level tour of a very comprehensive toolbox that's been in development for quite a while. So there's more that could always be shown here. But my goal really is to hopefully show you that these resources exist, this documentation exists, and the flow from your neuroimaging data to something like a general linear model or a connectivity analysis, and then to machine learning can be really, really streamlined by taking some of these libraries like Nilearn and using them to just move your data through from feature extraction to scikit-learn, for example, for the actual machine learning, and then model diagnostics, basically. So with that, I'm happy to take any questions that people have at this point, or happy to take questions on Slack as well. I see one.
We have time for one question. If anyone has a question here? Oh,
a new question, but a little bit of a reminder of the data leakage potential problems, Elizabeth. So when for instance, there was this idea of like trying to cluster things on your data sets, that's a potential like where you define the clusters using the whole data sets, and then you kind of learn on part of the data and then try to predict on the other side. But some of those, like those are some clusters that we define with the whole data set. That's like what is called data leakage, and so have to be careful with that, those sort of things. And another example of that you just described is that as a normalization aspect, sometimes PCA or variances or things are defined on the computed on the whole data set. And then, there's some information taken from the the test data there. So you have to be very careful in those sort of things. So maybe we can comment on that as well.
Yeah, no, absolutely. I think that's a really good point. Indeed, I didn't have as much time to go into data leakage as I'd like. I think it's an infinitely nuanced topic. But I agree completely that, in many cases, I think, Ariel, you might have brought this up in your scikit-learn lecture as well, about, dimensionality reduction can be a really unintuitive source of data leakage. And in many ways, you can think about some of these clustering as a form of dimensionality reduction. So the same principles, as you pointed out, JB, absolutely apply here. So you want to be careful exactly about how you define your train and test, what operations you perform where, making sure that you perform operations separately in train and test as opposed to across the whole data set and then splitting into train and test will go a really long way towards helping avoid that data leakage. But I think it's something where people, I have an example here about, just how a few different ways that we can think about it, but it's a much longer, I think, conversation. And I think making people aware of it and making people aware of where to start looking is probably the best general guidance. And then for the particular problem, really drilling down into, okay, what information is actually shared between your train and your test? And are you able to keep a validation set? The ones who can keep a validation set where it's really not touched at all, I think that puts us in the best situation moving forward. But yeah, something to always be aware of.
Yeah, and I think there's a question or two in the Slack, but I'm hoping we can get to those offline because we're out of time at this point. It's time to lunch. So let's all thank Elizabeth for listening off.